Have you heard that radiologists are all going to lose their jobs to artificial intelligence? Have you seen journal articles that mention convolutional neural networks and felt your eyes start to glaze over? I'm Sarah Jabauer, a physician and informaticist and the founder of Machine Learning for MDs. Today we're going to demystify how AI is used in medical imaging. You'll learn about convolutional neural networks, how they actually work, and why they're used for imaging specifically. You'll also be able to tell all your friends why radiologists will still have jobs and know what the limits of convolutional neural networks are in medicine. Artificial intelligence is used in medical imaging for radiology scans, ophthalmology, and pathology. And how do these things actually work? Machine learning uses a technique called convolutional neural networks to analyze these images. The words convolutional neural networks make it sound super complicated, but they use three main ways to turn images into numbers. First, they use a filter that tries to match the image. Then they use an activation function that makes the data easier to handle. Then they use a pooling function, which basically shows where the filter did the best job of matching the image. So let's say you're trying to keep your kid occupied for a few hours and you give them a stencil of a cloud and say, move the stencil slowly around this picture until the cloud exactly matches a stencil. That's basically what you're telling the computer to do when you start programming. Now imagine that that stencil is actually a 3x3 pixel set that goes over the x-ray of a hand, and it's trying to get the pixels to match the best possible way. These filters of pixels try to identify features like texture, border, and color contrast. Let's use this filter as an example. The filter is in the upper left corner and outlined on the big square by the green lines so you can see where it overlaps. This happens to be an exact match for the image, so you can see that when one pixel is white, then it will be multiplied by 1. You can also see that you then get the dot product in the far right square, which is also 1, 1 times 1. And then you see, as you go through all the squares, that for that particular filter, it matches perfectly. So it gets the highest possible score when you sum all of them, which is 9. And remember that this last example was a filter that was just on one square of an image. Now let's imagine that filter moving pixel by pixel all over the image. In this example, the filter is yellow, so it's the yellow box. It's placed over the right lower part of the green square. You can see that there's a small multiplication sign in the bottom right corner of each of those squares. The computer is multiplying the value of the filter pixel times the value of the image pixel. If you multiply those numbers together and then add them all up, you'll get a 4. And you can see that there's a 4 in the bottom right corner of the box on the right-hand side. That number 4 represents the sum of the dot products. Don't worry about the word dot products. It's a vector and you don't have to worry about the specifics of it for now. Now imagine sliding the yellow filter over the rest of the image 1 pixel at a time. You would calculate the dot product the same way each time the filter moved. If you did that all around the image, you would get the feature map, which is the pink box to the right. The feature map is the mathematical output of the filter, and it's called a feature map because it is mapping where specific features like straight lines are found in the image. Now, just don't worry if all this sounds super complicated. Just keep the general principle in mind. A filter of pixels goes around an image and looks for features like straight lines or curves. And it does it with math. Okay, the next thing to know about convolutional neural networks is that they use an activation function. And don't worry too much about the details of activation functions. There are a lot of kinds of activation functions, and I show some examples here because you might see some examples in the papers that you read. But the general idea is that they get rid of negative numbers for the most part and make the data easier to compute. The pooling function is where the filter matches the image the best. There are different kinds of pooling, but we'll focus on the common max pooling function. Max pooling just takes the maximum number, the biggest number from the filter, and condenses all the information about the pixels in that area into that one largest number. Okay, so to recap what we've learned so far, convolutional neural networks use three kinds of main operations to analyze medical images. First, they use a filter in the form of a small square of pixels that moves around an image and identifies the areas of maximum match between the filter and the image. Then there's an activation function that helps make the math easier. And then there's a pooling function that helps decrease data processing demands on the computer. Okay, so why do we use this particular kind of machine learning for images? Well, you notice that we took the information from multiple pixels and condensed all that information onto a smaller amount of information, a smaller box of squares, and that helps the computer move more quickly. It also helps to maintain and take advantage of spatial relationships and lets the computer recognize, for example, that eyes are usually next to each other and close to a nose, for example. And it also lets the computer tolerate some small variations in images, like the head turning slightly or the image being a little rotated. Okay, all that sounds great, but what problems do we see with convolutional neural networks in medicine in particular? First, the computer is trying to learn from an image in which most of the image is not the target image. So in photos of animals, the image is mostly a picture of an animal. But in medical imaging, the target image is a very small part of the whole image, like an abnormality in the brain, for example. Compared to the size of the information about the whole brain, that's a comparatively small amount of data. Next, these networks need to be trained on a huge amount of data. And there are just a lot more photos of cute cats than there are of brains. Also, many images need some kind of clinical context to make any kind of determination about the image. So a scan might be normal at one age and completely abnormal if it were from a younger patient, for example. Another idea is this idea of ground truth. So as doctors, we're comfortable with ambiguity, more so than computers are. We know that sometimes there will be something on a scan and we may just never know what that actually was. And computers have a lot of difficulty when there is no ground truth or no definitive way to tag an area of an image. So let's summarize what we've learned so far. First, most AI for medical imaging is going to be using convolutional neural networks, which is a subset of AI and machine learning. Convolutional neural networks maintain spatial relationships and decrease processing power needed for images. Second, all convolutional neural networks use filters, activation functions, and pooling functions. Current limits on convolutional neural networks in medicine include availability of large data sets to train the computers on, lack of clinical context, and lack of a ground truth